We will now start talking about a somewhat different way of reconstructing phylogenetic trees that's based on a type of statistics known as Bayesian statistics. This is a way of doing statistics that's different from the way most of you probably were taught statistics in high school or at university. Before we get down to the phylogenetic part, I'm going to give you a broad overview of what Bayesian statistics or Bayesian inference is. So for starters, Bayesian inference is very much about probabilities. So I'm going to just remind you about two basic aspects of probability theory that you probably know already, but that are important in this context. The first of them is conditional probabilities. Conditional probabilities play a large role, play an important role in Bayesian inference. So imagine that we're looking at this Venn diagram. So the box here represents the space of all possible events that we're looking at. The blue circle represents some event A. It has some probability that's indicated by the relative area of A in relation to the entire box. There's some other event B, which has a slightly larger probability. The B circle has a larger area. And then there's an intersection where both A and B are true, where both events A and B have happened. The conditional probability of A given B, as we say, the probability that A will happen, given that we know that B has happened, is expressed in the following manner. We write it like this: probability of A given B with a vertical line like this. And you can probably see from the Venn diagram that it's computed in the following manner. We know that B has happened, so we know that we're within this circle of B. And the question is then, what's the probability that A will happen, given that we know that? So we're within the circle of B. The probability that A will happen given this knowledge is simply the area of the intersection here, the area of this region where both A and B are true, divided by the area of all of B, or written symbolically, the probability of A given B is the same as the joint probability of A and B, the probability that both of them have happened, this area, divided by the total probability of B, this area. This is the definition of conditional probability and how to compute it. You can see that this equation can be rearranged quite simply into the one shown at the bottom here. If you multiply by the probability of B on either side, you see that the joint probability of A and B can be expressed as the probability of A given B times the probability of B. We'll use that in different contexts. There's one more basic aspect of probability theory I would like to remind you of, and that is the so-called law of total probability. So again, imagine we have this box representing the space of all possible events. Then we have some event A, and that is covered completely by these three mutually exclusive events, B1, B2, and B3. You can see from the Venn diagram that the total probability of A can be expressed as the sum of these three intersections between A and B1, 2, and 3, respectively. So the total probability of A is the joint probability of A and B1 plus the joint probability of A and B2 plus the joint probability of A and B3. But we know from the previous slide that these joint probabilities can be expressed in terms of these conditional probabilities that we just looked at. The joint probability of A and B1, the probability that both A and B1 are true or have happened, is the same as the probability of A given B1 times the probability of B1. Same is true for B2 and B3. So the total probability of A can be expressed as this sum of these terms, these conditionals, in the case where A is divided into a number of, or completely covered by these mutually exclusive events. We'll also use this expression later on in this lecture. So Bayesian statistics, the most central equation, the most central expression in Bayesian inference is so-called Bayes' theorem, which many of you will probably know from high school. Bayes' theorem tells us how to compute one conditional probability from the inverse conditional probability. So if you know the probability of A given B, then you can use Bayes' theorem to compute the inverse, the probability of B given A. And there's this quite simple expression for that. It's named after the Reverend Thomas Bayes, who lived in the 18th century, died in 1761. There's no good picture of Thomas Bayes, unfortunately, so you'll have to do with this plaque. There are in fact some pictures of Thomas Bayes circulating on most slides that you find on the internet and in many papers, but it turns out that that is not actually an image of Thomas Bayes, so we're going for the plaque here instead. You can incidentally see his tomb if you're ever in London. But enough about that. Bottom line is, Thomas Bayes originally published a paper where he used this expression as a way of thinking about a simple probability problem that in effect was using what we now call Bayesian statistics. Bayes' theorem, it turns out, is quite simple to derive based on basic probability theory, and in particular based on the definition of conditional probabilities. So you saw on the first slide that the conditional probability of A given B is the same as the joint probability of A and B divided by the probability of B. In the same way, we can define the conditional probability of B given A, the inverse, in the same way. The joint probability of A and B, but this time divided by the total probability of A. Now we can rearrange these two expressions in the following manner so that we isolate the joint probability of A and B on one side of the equation. So the joint probability of A and B must be the same as the probability of A given B times P of B, but it is at the same time also equal to the conditional probability of B given A times P of A. This means that we can set these two expressions on the right-hand sides to be equal to each other, which I've done here. If we take this expression and rearrange it slightly by dividing with P of A, then we finally get this expression, which is Bayes' theorem. So this follows fairly easily from the definition of conditional probabilities. Now, the main thing that's different about Bayesian statistics, that's different about Bayesian inference compared to regular ways of doing statistics, is the understanding, the interpretation of what probability means. The so-called frequentist interpretation, the classical interpretation, what you were probably taught in school, is that a probability is seen as the long-run frequency of some event in an experiment that you can repeat. So for instance, if you flip a coin 1,000,000 times, then the frequency of heads will be the true probability, or at least an approximation of the true probability that this coin will come up heads. In the Bayesian world, instead, probabilities are interpreted as a way of quantifying uncertainty, as a degree of belief. It's a way of saying, how much do I believe this is true, based, for instance, on some data. This way of using probabilities is actually something that many people use intuitively and that you will undoubtedly hear many times in regular life. For instance, if you're watching the weather forecast and someone says there's a 57% chance of rain, then that is in fact a Bayesian way of using probabilities. You're quantifying how uncertain you are about whether or not it will rain tomorrow. And based on that, you can then decide whether or not you want to bring an umbrella. This way of using probabilities is not, there's no easy interpretation in terms of frequencies there. There is only one tomorrow, so we're expressing our uncertainty about that in a Bayesian manner here. Now, it turns out that probabilities used in this manner, used as ways of quantifying uncertainty, as ways of saying how much we believe that something is true, there's actually a whole body of mathematical work arguing and attempting to prove that probabilities used in this manner is the only consistent way of doing what we call plausible reasoning. That is, reasoning about aspects of reality when we do not have enough information to do deductive reasoning. And that is, in fact, most of what science is about. We can very rarely use deduction to conclude how some system works. We collect some data. Based on that data, we try to infer or induct maybe how the system underneath works. And what these people are saying and what this volume of mathematical work is telling us is that probabilities is the correct way of attacking these types of problems. The first person that actually developed Bayesian statistics into what we now think of as Bayesian statistics and that used probabilities in this way, apart from Bayes, was really Laplace, a famous mathematician, French mathematician, that died in 1827. He published a great work on the theory of probability in 1812. And among the things that he did was that he essentially rediscovered Bayes' work independently and then developed it and used it in the manner that we now think of as Bayesian statistics. And one important aspect of using Bayesian statistics here is this fact that in Bayesian statistics we use probabilities as a way of quantifying what we believe to be true about nature. So in the case of Laplace, for instance, he was interested in trying to learn about the mass of the planet Saturn. So he had various data like gravitational influence on the moons and its rotation about the sun, etc., etc. And based on all of these data, he used these Bayesian statistical means to compute this result, which is a probability distribution over the possible masses of Saturn. This is in the units of 10 to the 26 kilograms, incidentally. So this is the outcome of any Bayesian analysis. Instead of trying to find a good point estimate of the mass, we are instead expressing our uncertainty about the real value of the mass as a probability distribution. So for any possible mass, there's some probability that we believe this particular value is true. There will be some maximum probability value, but there will also be varying degrees of belief in other possible values for the mass. And you can see from such a so-called posterior probability distribution, we can go in and say, okay, what is the probability that the mass of Saturn is between, say, 4 and 6, or between 2 and 1, etc. In each case, you can sum up the probabilities under that part of the curve, and they will tell you how much you should believe that this is the right value. So this is the outcome of Bayesian analysis, a probability distribution over possible values of the parameters in the models that we're trying to estimate parameters for. Now, to get an intuition about what role it is that Bayes' theorem plays in doing this kind of statistics, I have a small example here that may help elucidate some aspects of that. So let's say, to take an example, that we're looking at the Technical University of Denmark. We know that at the Technical University of Denmark, 16% of all people employed here are Swedish. That's probably not true. I'm completely making this up, but this is an example, so bear over with me here. Let's say 16% of all people at the University of Denmark, Technical University of Denmark, are Swedish. Let's say that 12.69% of all people at the Technical University of Denmark play the accordion. And finally, let's say that half of all Swedes play the accordion. Or stated in another manner, the probability that you play the accordion, given that you're Swedish, is 50%. So Bayes' theorem, I'll remind you, allows us to compute the inverse conditional probability in this case. So if you know the probability of A given B, you can compute the probability of B given A. So in this example, if we know the probability that you played the accordion given that you're Swedish, we can use Bayes' theorem to compute the probability that you're Swedish given that you played the accordion. We simply plug it into the formula I showed you on the previous slides, and we get this result. The probability that you're Swedish given that you played the accordion, according to Bayes' theorem, can be found by taking the probability of the inverse, the probability that you played the accordion given that you're Swedish, times the probability that you're Swedish, divided by the probability that you play the accordion. Plug in the numbers I placed up here, and you will see that that comes out at about 63%. So in what way is this useful in doing science? Well, you can see that the way that we've used Bayes' theorem here is actually as a stringent way of updating our degree of belief about some aspect of reality. Before we collect any data, if I'm just going to pick a random person from DTU, there's going to be 16% chance that that person is Swedish. If, however, I know that that person plays the accordion, then I can update my degree of belief about the nationality of the person, and I now think that there's a 63% chance that this person is Swedish. So I'm using Bayes' formula here to update my knowledge about reality in a stringent manner. And we could use this, for instance, imagine that you're at the DTU annual ball, you arrive at a table, you don't know who is going to be sitting next to you, there's an empty chair. Before you actually arrive at the table, you know that there's a 16% chance that you will be seated next to a Swedish person if people are distributed randomly. Once you arrive, you notice there's an accordion lying on the chair. The person is not there, but he's left his accordion. So using Bayes' formula, you can now, based on the observed data, the accordion, you can now update your knowledge about reality, and you now think there's a 63% chance that that person is Swedish, and you could then decide to actually sit there or maybe move on, depending on how you feel about Swedes. Nothing wrong with Swedes. We love them very much as Danes here. But the bottom line is, Bayes' formula is a way of coming from a so-called prior probability of knowledge about some aspect of reality to a posterior probability of how much we believe in that aspect of reality. And that's expressed in this formula, in this way of expressing Bayes' theorem. If instead of A and B, we now put H and D, where H means hypothesis and D means data, then we can see the way that it's typically used in doing science. The probability of the hypothesis here is what we call the prior probability of the hypothesis. That's how much we believe this hypothesis is true before we've collected the data that we are now in the process of analyzing. The probability of the hypothesis given the data is what we call the posterior probability of the hypothesis. It's the probability, the degree of belief we have in this hypothesis after we've seen some data that we've collected. The way that we update our knowledge from the prior probability to the posterior probability is via this equation, and the important term in this context is this one, the probability of data given the hypothesis. And as you may recognize, this is actually a term that we've run into previously. This is namely the so-called likelihood. The probability of your data given your model is what we call the likelihood, and you've even tried to compute likelihoods manually for the case of a phylogenetic analysis. So, as long as we have a prior probability and as long as we can compute the likelihood, we're able to compute the posterior probability. P of D here is the so-called marginal probability. I'll say something more about that in a second, but it's essentially a normalizing constant, so different values here will sum to 1. One other word about the way we write Bayes' theorem. There's a number of different ways in which we can write it that maybe puts emphasis on different aspects of how it's used. So the top version that I've written there is the same that was on the previous slide. This way we're saying that we update knowledge about some hypothesis H based on the data D. For instance, updating our knowledge about whether or not the person we will be seated next to is Swedish or not. There's another version on the second equation here. the probability of Wi given D. This is, in this case, the focus is on learning about the W, different possible parameters within some model. It could be, for instance, branch lengths or nucleotide frequencies or whatever. And the subscript I tells us that there are many, in this case, discrete possible values of the parameters. And for any given set of parameter values, the posterior probability of that particular set of parameter values can be found like this. We will then get a posterior probability distribution over possible parameter values using this formula. This is exactly the same as with the example with the Laplace and the mass of Saturn. He had that single parameter in his model, the mass, and the result of his analysis was a posterior probability distribution over possible values of the mass. But that's true for any parameter in any model you might analyze in this way. Sometimes you'll see it written in the manner that's below. This just stresses the fact that the parameters W here belong to a particular model. For instance, if you have parameters A and B that are the parameters in a linear model and the slope and the intercept in a line, then you might want to explicitly say that the A and B here belong to that linear model. You could also have, for instance, a polynomial model with some other parameters, A and B, and maybe C and D or whatever, and you would then say that these parameters belong to that other model. Finally, the P of D that we have in the expression up here, the total probability of the data, this is the total probability of getting the data under any possible value of our parameters. In any possible way in which reality could be put together, how would the total probability of getting the data be? In the case of discrete data, like we have here, discrete parameter values, P of D can be found according to the law of total probability by summing up the probability of data D given each possible set of parameter values Wj. So let's say there are n different possible sets of parameter values. Then for each possible set of parameter values, we find P of D given Wj times the probability of Wj. So sum up all of these, and according to the law of total probability, we will have the total probability of D. Briefly, I should maybe mention that just as we can find, for instance, posterior probability distributions over possible parameter values within a model, we can also use Bayes' theorem to compare different models. So you can have two completely different models and then actually compute so-called model probabilities, which tells you which of two different hypotheses to believe more in. There's a detail, the equation for doing that is, as I've indicated on the top here, is just a simple use of Bayes' theorem. But I should point out that in this case, the probability of your data given some hypothesis H1 is found according to the the denominator on the equation you saw on the previous slide. I'm not going to go into this, I'm just mentioning it because you may run into model probabilities at some point, and then you have this slide to look back on. So at this point, I suggest that you do the exercise where you get the opportunity to manually compute posterior probabilities for a simple toy example, since this will give you a stronger understanding of the whole process of using Bayes' formula for computing these probabilities.